Okay, welcome everyone. So we have with us today currently from Mexico City. Currently from Mexico, not city. On her way eventually to the Technion, my former student Sarai Hernandez Torres. And, your screen is already shared, so you can start.
Yes, well, thank you very much. I'm very happy to see you all and to finally tell you about some of the work that I did during my PhD. So this is on the scaling limit of uniform spanning trees in three dimensions. And this was with Omer and also with David Croydon and Daisuke Shiraishi in Kyoto. So the plan for today is the following. First, I'm going to go through the basic definitions of uniform spanning trees and loop arrays random walks on a finite setting. And then we will get started with scaling limits in the case of a loop arrays random walk. And then we will jump to scaling limits of uniform spanning trees on a lattice in dimensions 2 and 3. And then we will get into the proof. So I really want to tell you about some bounds that we can get on the intrinsic ball. And more or less, this would be the first hour of the talk. And after that, we will have a 5 minutes break. Then we will to something I rarely have a chance to talk about, and these are the path properties of loop arrays random walks in 3 dimensions. So let's start with the basics on uniform spanning trees. So our setting is on a finite graph that is connected, just like the one that I have here on my right. A subgraph that goes through all the vertices of it and doesn't have any cycle is a spanning tree of G, like the one that you have now on the picture. So, well, it doesn't have, well, the selection of spanning trees is finite since our graph is also finite. And we can, without any doubt, put a uniform measure over this finite collection. And a sample from this uniform collection is a uniform spanning tree of U. So let's say that this is the one that I got. But if my graph is very large, it will still be finite by large. It would be to get one of these samples because the number of trees would be gigantic. So we are interested in a way to sample these trees without having to go, well, through enumerating all of them. So an important fact is that if I take 2 points on the spanning tree, let's say X and Y, then the random path that connects X and Y on the spanning tree has the same law than a loop arrays random walk. So the first step to understanding how to draw a uniform spanning tree is to first see what are these loop arrays random walks. So this is the next step of what I'm defining today. So we still are on the context of a finite and connected graph G, and I am going to consider a simple random walk on it. So let's say that I have a path like this one. Every step is independent, chosen uniformly between the neighbors at the current position. And let's say that this path stops here. So the loop arrays random walk is going to erase all the loops that I have on my path chronologically. So I started here, and then my walk made this loop. So I'm going to erase it. And I will only take the last exit edge from it. This was also a last exit edge. This we will also consider it a loop because it's backtracked. And I'm only going to consider this again, that is the last exit edge. And I continue. And this edge, I'm going to take it because although it said something on the past, is a loop that I already erased. So this is the importance of the chronological order. And my path ends here. So as you can notice, the loop array's random walk starts at the same position and finishes at the same point where my simple random walk finished. So this model was introduced by Greg Lawler in 1980, and this is the loop array's random walk. So now we know how to draw our paths on the tree, and essentially what we want to do is that these are our branches of the tree. So the following algorithm will tell us how to effectively draw our uniform spanning tree with loop arrays random walks. So this is Wilson's algorithm. And the first step is to all the vertices of our graph. We know our graph is finite, so we have from x naught to xn. And we're going to take the first vertex, x naught, and this is going to be T0. So this is the first tree that we create. And then we take the following algorithm, well, in our image, x1, and then want to consider a loop array's random walk that starts at x1 all the way to the first time I hit what I have created at this point, t naught. What all the edges on the walk to my next tree, T1. So this is what I have built so far. And then I go to the following vertex on my enumeration, x2. In this case, it's already on the tree, so I have nothing to do, and I could have to ignore it. And let's say that x3 is the next one on my enumeration. And again, I consider loop array's random walk starting at x3 until the first time that it hits what I have built before, and so on. So I'm going to finish, and when I have sampled all the, well, when I have used all the vertices on my subtree that spans all the vertices of T. And the theorem says that Tn has the same distribution of the uniform spanning tree of G. So now we know how to go from loop array's random walk to uniform spanning tree. So, well, the previous was just a picture that I draw on my virtual blackboard, but this is a real one that from Mike Bostock webpage. So you can look for his webpage where he has like a lot of nice code on how to build, well, how to use them to construct the uniform spanning tree. So let's now focus on a more humble objective of just looking at the scaling limit of a loop array's random walk. So here it's easier because it's only a path, well, and well, by definition, what we originally have is a collection of vertices on our lattice all the way to the last one. So it is easy just to take some interpolation. From the path, we could get a curve. So we can assign that we're going to take time 1 to go from nearest neighbor vertex. And we are familiar with spaces of curves, and then we only have to choose some metric over which we're going to consider our scaling limits. So one choice is that we're only going to think about metrics for the traces of our curves. I am only looking at the shape. So for example, if I have these two curves, like this green one and the orange one, and let's say that the distance between these points and between any 2 points in this oval is epsilon, then if I am just looking at the trace, they are quite close, because for any point on the orange path, I can find a point that is nearby on the green path and vice versa. But well, this is only capturing one aspect of our curves, and we'd also want to consider the parametrization. So in this case, the parametrization says that this curve, the green one, starts at the top and finishes at the bottom. Meanwhile, the orange one stops at the top and finishes at the top. So if we want to consider the parametrization, then these two curves are no longer close, but they are far away, because they first end up at different places, and also they not necessarily go at the same speed. So if you want to have a choice for one metric for parameterized curves, we could pick that the distance between gamma 1 and gamma 2, where gamma 1 is the orange and gamma 2 is the green one, would be the difference between T1 and T2, where T is the length of each of these curves, plus what is the difference of the positions as we go through them. As S is between 0 and 1. So this is one possible choice of many for a metric for parameterized curves. So if we want to consider the scaling limit of a parameterized curve, then we need to take into account what is the proper normalization that we have to put to the parameterization. So this is where the growth exponent of the loop race random walk is relevant. And I am going to denote by Mn the number of steps that the loop race random walk gamma takes to exit a ball of radius n. I would say that the growth exponent exists is if we can, in some sense, say that the expected value of Mn is approximately n to the beta. So in 2 dimensions, Rick Kenyon was able to prove that the growth exponent exists and is equal to kappa with the value of 5/4. So the way that he made this precise is that he proved that the limits of the logarithm of the expected value of Mn. So this is going to give us exponent kappa. This is equal to 5/4. And in the same sense, more real exponent of the loop race random walk now on 3 dimensions exists. But we don't know what's the exact value as in the 2-dimensional case. We only have bounds that come from some work of Greg Loller that says that this growth exponent beta is strictly larger than 1 and smaller or equal than 5/3. And there's some simulations of David Wilson that says that this should be somewhere close to 1.624, ... And there's no reason to believe that this should be, well, that beta should be a rational number as kappa is. But instead, the expectation, well, what we think is that it's going to be some irrational number. But at least we know that beta is, well, the growth exponent, that it exists, and this is going to be in all our renormalization as we take the scaling limit.
Right.
So for the 2-dimensional case, we know, well, quite a lot. Someone wanted to say something?
Oh, yeah, I wanted to ask if is it known that Mn is concentrated around the expectation? So is that also a high
right.
probability?
I'm going to go there later today.
Okay.
Yes. Yes. I have another slide where I'm talking more about, well, the growth exponent is like very important piece, so it will appear again later today. But it is concentrated in 3 dimensions and of course in 2 dimensions. But now let's go to what we know on the scaling limit of the 2-dimensional loop race random walk. So here we know that this scaling limit exists, and we also, to what it converges to the Schramm-Lohner evolution with parameter 2. And this was first proved by Greg Loller, the Schramm, and Wendelin Werner in the topology for unparameterized paths. And there is a more recent preprint of Loller and Bicklund where they consider the scaling limit with the metric for parameterized curves, where the loop race random walk goes with its natural parameterization, and the Schramm-Lohner evolution is parameterized with Minkowski constants. But even furthermore, we know not only that this is the scaling limit on the lattice, but we also know that it converges in a lot of situations, like if we have a planar graph, as long as the simple random walk converges to Brown motion, we also have the convergence of the scaling limit, that the scaling limit of the loop race random walk is SLE. So two-dimensional case is quite well understood. But it was a breakthrough when Gary Kosmak proved that the scaling limit also exists in the three-dimensional case. So he had to put some hypotheses to prove this convergence. So first, he was restricted to a polyhedron. And this polyhedron is the one that is scaled. So let's say that I choose a polyhedron like a cube. And here I am rescaling my lattice. So the distance between points on the lattice is 2 to the minus n. And n goes to infinity. So at each scaling, I can consider the loop race random walk. And that starts at some interior point of my polyhedron. And then is stopped at the first time that it exits the polyhedron. So the theorem is that this law, the law of these curves converges weakly with respect to Hausdorff topology. So it means that we have convergence in shape. And more recently, Shingili and Daisuke Shiraishi improved this to include the parametrization of the loop race random walk. So in their work, they consider a ball instead of a polyhedron, and now this is the ball that is going to be a scale. So we're going to consider a fine lattice here, and for this fine lattice, we are going to take a simple random walk, loop race random walk that starts at some point in the interior, let's say 0, and then it's stopped at the first exit from the ball. So we parameterize with respect to the growth exponent, so we get something meaningful on the limit. And the law of this reparameterized curve converges weakly with respect to uniform convergence topology. And well, they consider a ball, but their work uses results strong enough that it can easily be improved to a polyhedron. So as long as this has a smooth boundary, there is no problem with considering a different domain. And here we also have the convergence with respect to the uniform topology. So this is what we know for scaling limits of loop race random walks. Yes, is there another question?
Could you explain a bit more what exactly is a polyhedron? Is it a union of cubes?
Yes, well, here I just took a cube, but if you want to have something more explicit, you can say that a polyhedron P is going to be a union of B, where B has its vertices on, well, here you can ask an integer to have some meaning. After all, what you are scaling is the lattice here. So it will be a little bit different if instead of the lattice, I were scaling the polyhedron itself, which is another choice.
Okay, thank you. Thanks.
Well, B is a cube. Oh, I also use B for a ball, so maybe this is not the best notation. So I want a cube with vertices on integers.
Right, thank you.
Yeah, this is actually, if I'm scaling the lattice, is more easy just to take any polyhedron. It becomes, well, it's for me a little bit more complicated to visualize if I am scaling the polyhedron instead. But well, clarify that. Let's go to scaling limits of uniform spanning trees. So now we understand how our branches scale, so we want to see what happens with the whole tree. And there are two operations that we have to do. The first one is that we need to specify what we mean. What do we mean by choosing a span tree on an infinite lattice, like set D? So we have to say, well, we take the limit on the infinite volume, and then we're going to take the scaling limit. So we need to clarify what we mean. What do we mean when we take delta, the distance between nearest neighbor vertices, going to 0. So let's start with taking the infinite lattice. And this is more or less straightforward because we're going to do what we always do on a model of statistical mechanics that we have defined on a finite graph. So what we're going to take is a collection of graphs, lambda n, that is going to contain one into the other, growing larger and larger, so that it's going to take all the vertices of set n. And for each one of these graphs, lambda n, we have some uniform spanning free measure. And we take the weak limit of this uniform spanning free measures, and this defines the uniform spanning forests. So I will be more explicit now. So we have one of these boxes, lambda n, and we consider some finite set of edges B. And there's some probability that this finite set of edges B belongs to the uniform spanning tree of lambda n. And as I increase the size of my boxes, then the number of paths available between these vertices is larger, so the probability that I have this specific set of edges B is smaller. It means that this probability converges in the limit as n goes to infinity. And I eventually cover all the vertices on my graph set n. So I define that the uniform spanning forest takes this limit probability for containing this set of edges B. So by definition, I took my exhaustion lambda n, so that is going to pass through all the vertices on the graph. So the limit object is going to be supported on graphs that also contains all the vertices of set n. And also by definition, if I consider a finite cycle is not going to be zero here. So in the limit measure will also have probability zero if, for finite cycles. So I know that I have a subgraph that goes through all the vertices and that doesn't contain finite cycles. But something that I cannot guarantee is that if I take the distance between A and B, this is not necessarily tight, so this may go to infinity. And in that situation, if the distance between A and B is infinity in the limit, it means that they are in different connected components. So I'm not necessarily get a tree on the limit, but what I get instead is a spanning forest. So the existence of this limit was proved on the infinite case, but well, on the case of set D, it was proved by Robin Pimentel in '91. He not only proved existence, but also its uniqueness. So the first way that this is unique is that it doesn't really matter what is exhaustion lambda n that I take. But furthermore, it doesn't matter the boundary conditions that I have on the uniform spanning tree measure. Here I took free boundary conditions, but you could have also taken wire boundary conditions or a combination of free and boundary conditions. So in any case, you will always get the same limit measure. Furthermore, he also proved that the uniform spanning forest is going to be a tree, and in that case is the uniform spanning tree, and that's how I'm going to call it, if and only if the dimension is small enough. So if the dimension is smaller or equal than 4, then what I get is a tree. And this talk is only concerned about dimensions 2 and 3. For that reason, I'm just going to stick saying uniform spanning tree. But now you're warned that if this is greater than 4, then actually a number of connected components is going to be infinite. Good. So now that we know how to take our trees on an infinite lattice, we want to take the scaling limit. But to take the scaling limit, we need a metric space. And for this reason, we need to be a little bit more fancy in the way that we define our uniform spanning forest. So we can consider a metric and we get something meaningful in the limit. For this reason, I'm going to consider the uniform spanning tree as a metric space, but not only that, as a metric space that has a measure, that has a root, and that has a special embedding. So I'm going to denote by U the space of points on the uniform spanning tree that now is going to give me this abstract metric space. And naturally, there is an intrinsic metric defined on it. So if I have 2 points A and B, there is, because this is a tree, a unique path between them. So this path has some inherited distance from the graph. So if I denote that the length of each edge is 1, then the distance between A and B is just 1. I mean, sorry, I don't know how to count this tree because we have 3 edges, 1, 2, and 3. So this is a natural distance for the 3. And then we also have a natural measure for it. So for a measure, we're going to assign for each point that identifies as a vertex, weight 1. So you measure of a set, we only need to count vertices are there. And here we obtain a measured metric space, but we also want to remember the way that it was embedded on our Euclidean space. So we're going to keep a function phi that is the identity. So we're going to take the identity on the vertices and interpolate along the edges. And finally, to have everything well defined, we're going to take a root that it could just be 0. So we know that the uniform spanning tree will have the structure of a tree. So when we look at it as a metric space, this is in fact a real tree. And we're going to call the tuple of these 5 elements a measured rooted spatial tree. So BOLT is a collection of all the measured rooted spatial trees. And these are the elements that are a complete and locally compact real tree. So here, of course, this real tree that I'm considering is not compact, but is locally compact. So I know that there are some definitions where real tree is compact, but here I'm pushing a little bit more to allow the uniform spanning tree to be one of them. And that is, it also has a locally finite Borel measure, which is the case of the counting measure, that also has a continuous map onto the space RD, and that is rooted. So this space, BOLT, is a separable, metrizable space. I'm not going to write down here what is the exact metric that we endow to BOLT because it's a little bit complicated, but what you need to know is that it incorporates the Gromov-Hausdorff distance to measure between metric structures, the Prokhorov distance to measure differences to the measures, and that we measure differences on the continuous map with uniform convergence topology. And of course, well, we can consider Gromov-Hausdorff distance with the root, so that we also measure how far away is the root to measure root of the space trees. And we're going to keep, to consider this set for our space of trees because it has a very nice criterion for tightness. Sorry. That this was proposed on Abraham Delman's and Huschet work. And for the specific case of the uniform spanning tree, it was used by Martin with David Croydon and Takashi Kumagai when they were studying 2-dimensional USTs and their sub-sequential scaling limits. So it is for the availability of this tightness criterion that we are using this framework, just Martin and his collaborators did. And now I will specify in the framework of measured rooted spatial trees, what do I mean by the scaling here I have my picture. If I were just to draw a picture, then it is very clear what the scaling limit looks like. It looks like I'm zooming out the space. So the distance between nearest neighbors vertices is smaller, so this would be delta. And originally it was only 1. On the tree as a measure metric rooted spatial tree, it means that my embedding is scaled by delta, because this is exactly what is happening to the space. And then my measure is scaled by delta to the dimension of the space, because that's the amount of vertices that I am going to get after the scaling. But for the distance, I have to be a little bit more careful. Here, if I am only at distance 1, then the distance between these 2 points in the Euclidean metric is 3. So the Euclidean distance between x and y is 3. And here I was lucky, and the distance inside the 3 is also just 3. But here, well, the Euclidean distance is still the same. But now my edges are only delta, and in this case, I actually took delta equal to 1/2. So I have to go through a longer number of edges to get to the same distance. So in effect, I'm scaling according to some growth exponent. So in this case, I had to go by this more complicated path to arrive to the same spot. So I have to rescale by some exponent, that is the growth exponent that corresponds to the path between 2 vertices of the uniform spanning tree. But lucky for us, this path has a distribution of the loop radius random walk. So what we are going to scale by is by beta, where beta is the growth exponent of the loop radius random walk. So to take the scaling limits here, what it means on my spaces is measured rooted spatial trees, is that I'm scaling my distance by delta to the beta, the measure by delta to the d, and the embedding by delta. So under these scalings, we can talk about what is the result for the uniform spanning trees. And we start with a 2-dimensional case, which is also very well understood, starting from the seminal work of Oded Schramm in the 2000, in this paper where he defined the Schramm-Lohner evolution, all the way to the more recent work where the full convergence was proved. So this is still on the framework used by Martin with David Croydon and Takashi Kumagai of these measured spaces. And we take the scalings that we saw in the previous slide. So the first result is that, as you may have guessed, we get tightness of the spin as we scale them. And Nina Holden and Shin-Sun proved that we get the full convergence as delta goes to 0. And not only that, we know that the limit object is described with Schramm-Lohner evolution curves. And this is from what we know of the work of the translator with Reckler and Bengelin-Werner. So here we have a complete picture of the 2-dimensional scaling limit. And this is what we got for the 3-dimensional scaling limits. So we are now on the 3-dimensional setting where beta is our growth exponent, and this is the one by which we rescale our distances, and we rescale delta to the cube, our measures, so delta the embedding. So for these objects, we get that their laws are tight, and then we consider particularly dyadic scalings, then this law converges. So here, the restriction on the scalings comes directly from our restriction on the scaling limits of loop radius random walks. Because since the work of Gary Kozma, it was particularly for dyadic scalings. So this restriction will give us our restriction here. Now let me tell you a little bit about how we prove this result, tightness and convergence. First, tightness, we use the same criterion that Martin with David Croydon and Takashi Kumagai used. And one important element of this criterion is the volume of the intrinsic ball. So this is something that I would like to talk more later today. For the convergence, once that we have tightness, it suffices to show the convergence of subtrees. So these are subtrees spanned by a finite collection of fixed points. So, and this is under, well, the setting of the dyadic scaling. And are shared by both tightness and convergence of the dyadic scalings is that we're going to use Wilson's algorithm rooted at infinity. So this is a version of Wilson's algorithm that is, well, that works for our infinite lattice as set 3. And then we're going to use that, well, the loop race random walk converges to its scaling limit. But not only we need the convergence in the scaling limit for the loop race random walk, we also need that this has good properties, good path properties with high probability. So, well, this is a little bit vague. What do I mean about good path properties? But this is something that I want to talk on the second part of my talk after the brief break that we can take. Of the sub-sequential scaling limits that we get on the three-dimensional space. So let's denote by U one of these sub-sequential limits. And well, what we get is a metric space that is complete, locally compact, that is also a real tree. So we do not have embeddings of the circle on the metric structure of our tree. But not only that, we also have a unique isometry of the full infinite ray that starts at 0. So in that, if I have my origin 0 and I make a path that goes to infinity, then there's only one of these paths. So a way that we can think about this is that there are no infinite cycles. If there were an infinite cycle, we would have 2 paths that go to infinity, but instead we only have 1. So this is at 3, even when we complete the space well. And we have a space, so one of the first questions that we can ask about the geometry of it is on its Hausdorff dimensions. So again, this is one of the limits. And Hausdorff dimension is 3 over beta, where 3 is the, well, dimension of our 3-dimensional space, and beta is the growth exponent of the loop race random walk. The way that you go to prove this is that it suffices to show that we have good upper and lower bounds on the volume of our intrinsic balls. So in general, when we want to prove the Hausdorff dimension of something, we want to find a measure that gives us good bounds for any of our intrinsic balls. So it turns out that the counting measure, well, as we take the limit, we obtain this measure for the sub-sequential limit. And this one is the one that helps us to find the Hausdorff dimension. And it is close to R to the 3 over beta when the dimension of the ball, when the radius of the ball is R, and we have some logarithmic corrections because we want this estimate to hold uniformly for all the balls of our metric space. So this is for any X. Well, now we see that we want, again, an estimate over the volume of the intrinsic balls. Uniform control over the volume for intrinsic balls. So, something went wrong. I have to share again my screen. But now I have just arrived to a point where I can talk about these intrinsic balls. What can we say about them? So I will just talk about the easiest proposition, but this is one of the assumptions that you need to prove to obtain the tightness of the scaling limit. And this says that if I compare the intrinsic ball, PU, with the Euclidean ball, if I'm scaling properly, then this ball of the intrinsic metric of the uniform spanning tree is contained on the ball of the Euclidean metric. So I want you to compare with the equivalent proposition for the loop race random walk. So, and this is where appears the question of G-non. So we know that we have tightness over the number of steps that we need to take to reach the boundary of the ball of radius n. So Mn is the number of these steps. And with high probability, we know that Mn is at least n to the beta with some correction lambda -1, that this will change how big we want to be this probability to be. But this tightness of the number of steps to exit a ball of radius n is equivalent. Well, this is a version of this proposition, but for the loop race random walk. So let me show you why. So if I say that then this number Mn is at least lambda -1 n to the beta, it means that if I'm looking to the intrinsic ball, but for the loop race random walk, when I look at this intrinsic ball at, well, this is n to the beta, this is contained on the Euclidean ball of radius n with high probability. And here I'm writing n instead of delta, but of course I can set n to be delta -1. So if I rewrite this, what I would get is that the intrinsic distance for the loop race, when I consider the ball with respect to that, this is in the Euclidean ball. So as you can see, what I want to do is to upgrade the tightness that I have for the loop race random walk to obtain the equivalent statement, but for the uniform spanning tree. So our strategy to prove this sort of a statement is to sample the uniform spanning tree with Wilson's algorithm rooted at infinity. And then we're going to work on the event that all the loop race random walks that we use in Wilson's algorithm have good properties. And by good properties, I want to have some hitability. It means that a loop race random walk is going to be hittable by an independent simple random walk. So I will clarify this in a moment. And also that it has the property that we're looking for. In this particular case, that they have the typical length, that the number of steps that this loop race random walk take to exit a ball of radius n is at least of the order of n to the beta. So let's see how this looks like. First, let me show you how Wilson's algorithm rooted at infinity works. So here I am not really interested in sampling all the vertices of my tree, but what I want to do is to consider some vertices, and I want to sample a subtree that is spanned by these vertices, and it has the same distribution of the subtree on the uniform spanning tree spanned by them. The first step of the algorithm, of course, is to take a loop race random walk. In this case, you can see why the name rooted at infinity makes sense, because our first loop race random walk is infinity. So in a sense, I am not going to stop until I meet the root. And in this case, the root is infinity. So this is an infinite path. And I continue in the same fashion as Wilson's algorithm did. So then I take the next vertex. I consider a loop race random walk until it intersects what I have built at this point. And I add it to my new tree, and so on and so forth, until I go through all the vertices that I originally picked. So the theorem is that this tree that is spanned by these vertices is equal in distribution to the tree that I would find spanned by them on the uniform spanning tree, including its path to infinity. So how do we use it to prove a proposition for our scale trees? So here I am on the setting on this scale lattice. So the distance between nearest neighbors is delta. And I am not going to, of course, sample the uniform spanning tree for every single one of these small vertices, but instead I'm going to take a mesh. So this is going to be a collection of vertices that are, let's say, epsilon away from each other, and epsilon is going to be larger than delta. So these are the vertices for which I will have control on what happens with the uniform spanning tree. So, let's say that this is what I get as the uniform, from Whistle's algorithm as I sample these vertices that I choose at the beginning. And I want to condition on an event that has high probability. And that is that each one of these loop race random walks that I got are hittable. And the reason why it's useful is that if I were to continue finding more elements of my uniform spanning tree coming from this, other vertices that are nearby at some distance epsilon, I know that these paths would be small because the way that this is generated is that I start with my point here that is purple, and the way that I go is that I take an independent simple random walk. But if the red paths are hittable, it means that this purple path is also small. So the point is that the behavior of my uniform spanning tree is going to be controlled by the red paths, and the purple ones are not going to be significant, and it's going to be okay. So I can consider that I have the good property that I want to upgrade from loop race random walk to uniform spanning tree. So in this case, that they have this typical distance. And there's more to talk about this in the last part of the talk. So this is a way that I am going to fill my space. I call it a filling strategy. But now let's see how it works in the specific case of the proposition that I want to prove, that is that the intrinsic ball properly scaled is contained on the Euclidean ball. So this is a sketch of the proof. Here, as you can see in the proposition, I have scales on the balls, but for the sketch of the proof, it's better to scale the lattice because it allows me to have a smaller, smaller drawings. So here I'm working on a small graph that has distance delta. So it means that this Euclidean ball that has radius delta -1 on the Euclidean space set 3. So this is proposition on set 3 is equivalent to the unit ball when now I am scaling the space, but it's easier to draw. So what I want to avoid is to have the following situation. Something that would be bad is that I have some x. So x that is not on the Euclidean ball of radius 1, but that somehow has a small distance in the tree to the origin 0. That is much smaller than delta to the minus beta. Somehow like goes quickly, like this would be unlikely and unlucky. And we want to show that this does happen with high probability. So this is the situation that we want to avoid. And the way that we're going to go through is that we're going to sample our tree on annuli. So we have these annuli that are getting closer and closer to the boundary. So I define AK to be B1 minus 1 over, 2K. So to this analy is the spaces where I'm going to apply my filling strategy. So I'm going to consider nets, the ones where I am going to consider the Wilson's algorithm. And these nets are also going to decrease as 2 to the minus k. And well, of course, I am restricted by how big this delta is. So this is going to be for k equal to 1 to some k naught. But this k naught, what I want to guarantee is that if I look to the boundary of my ball 1, that this is going to be contained on the last of my nets. So this is one very small net that is only going to be just very close to the boundary, the k naught. So let's start with the first one of this analyze. So this is A1, and in this case, this is my unit ball minus ball with radius 1/2. And here I consider the first one of my nets, T1, that this is just T to the 2 minus 1, lambda minus 2. I mean, lambda minus 1. So here these points, what they indicate are the points where I'm going to start Wilson's algorithm. So starting at the origin, this is going to be the one that is going to contain this infinite path that goes to infinity. And well, I'm not going to draw it, but for each one of these red dots, I will generate Wilson's algorithm. So there is going to be loop race random walks that are going to eventually join gamma infinity. And for each one of these loop race random walks, I'm going to ask these conditions that I already told you, that are heatability and typical length.
Sorry, what's the spacing
But
between
not only that, I would also ask the spacing between them.
Between the red points, yeah.
Of the order of lambda minus 1 to the minus 1, I think.
Okay, thank you.
Yeah, this is, and well, this has radius 1/2. So this is still at some, well, but the thing here is that the space is scaled. So there's even more points there on the lattice. But I am also going to ask that with high probability, if I take one of these points, x, as it finds its way to the path gamma infinity, it's going to avoid this ball that is going to be lambda minus 4. So what I want is that with high probability, when I look at the path between x and gamma infinity, so this is x and this is the path gamma infinity, this is going to avoid this other ball lambda minus 4 with high probability. So I don't want to get too close to the origin. And this is for all x on the first one of my points on the net. And I will continue in a similar fashion for the rest of my analy. So if I get AK, so I will get a more fine, well, a finer mesh. So I still have, so here, oh, sorry. So here you see that there are like more small points closer to the boundary. And now what I'm going to ask to these smaller points is that they do not get, as they find its way to gamma infinity, is that they do not get close to the ball of radius 1/2. And I continue from K until I get to K naught. So what I will get is that with high probability, if I look at the intrinsic distance between a point Y here that is in one of these meshes that I have built from from 1 to K naught. This is going to be at least some lambda to some exponent. Actually, this C is equal to 9 delta minus beta. But here what I asked is that the the interior boundary of B is in the last of these meshes, K naught. So it means that if I'm taking X, a point in the exterior, the path to the origin is going to go through one of these points in the interior boundary. So this is all what I need to say that the distance between 0 to X, this X that is not on the ball, B1, is going to be at least of the same order than this, at least lambda minus C delta minus B, because the points on the boundary already satisfy this. So this is for all points that are on the complement with high probability, which implies the statement that I want to prove. And this is how you get this bound on the intrinsic ball. So this is the first part of the talk, and I think this is a good moment for us to take a break.
Okay, thank you. So I guess we can have any questions now.
So as the annuli get thinner and thinner, do you really get down all the way to the microscopic scale?
Oh, well, here I am at scale delta minus 1.
No, I mean the spacing between the red points gets smaller as you go to the thinner annuli, right?
Yes, well, it's going to be thinner, and also I change, well, what is the spacing of the nets? So the nets is going to be, this is the first one, it's also decreasing exponentially to the minus K. And there's some K at which I cannot go any further because I am not looking to go all the way to, I'm not moving delta is fixed. So there's some point, some K at which I cannot go any further. But really, it's because I already got all the points on the interior boundary of the ball.
So, yeah, so Sarai, by the way, your video, I think for some of us is very choppy. So
yes,
I'm not sure if there's anything.
I think it's my
connection. You can do with...
No, unfortunately, there's not much I can do. I'm not sure why. Usually it's better.
So it's unfortunate. At least the sound is good. So we can always hear what you're saying.
Oh, that's good. Yes, I noticed. It seems to be a delay.
Yeah. So.
Sorry, I have another question. So you said you want to control the probability that the path doesn't go inside your balls, right?
Right. Mm-hmm. But the points in the exterior, well, in the complement of the ball. I don't
Sorry,
want
could you maybe
go...
restate the event again? Maybe I just missed. So what do you want to control the hittability and the probability that you do not hit the ball of bigger and bigger balls? Is that right?
Oh, no. I think this is what you are wondering about. Let me find the... right one. So this is the first annuli. So what I want to avoid is that, well, here I have my first path from the origin. And this is the path that goes to infinity. So I want to X, it avoids this ball. But this is for A1. But later, for these other annuli AK that are closer to the boundary, I'm not going to ask that they avoid the original ball of radius lambda minus 4, but instead I will be satisfied if they avoid the ball of radius a half. So the points that are closer to the boundary have, are already closer to the boundary, but I don't want them to get too close to, radius half of the ball, of the origin. And this is going to be the same for all, the other annuli that I find.
And you don't care if they go very far out of the ball? I mean, very far towards infinity? You don't care about that?
No, that's not going to be a problem, because in the intrinsic distance, it means that, well, they are going to do something like this. But I'm caring here about balls that are around 0. So at the moment, I just care about intrinsic ball close to the origin. So from the point of 0, this long detour is only beneficial because it means that the path is longer. And later on, you improve these estimates for any point on the space, but this is the easiest one, the one where you just consider the intrinsic ball around 0.
Okay, thanks.
So I think we can at least start again in just a minute or so. Now, Sarai, how long did you plan the second part?
15 minutes, it's shorter.
Ah, so it's, okay, so it's not two equal lengths, okay.
Oh, no.
Since, since this first part was more than I expected for a first part, so. Okay, and for whatever reason, the video is now working very fine.
Oh, that's a problem. It's never reliable.
Yes, it's indeed tricky often. Should we continue?
Sure. Well, I'm very happy that I have the opportunity to talk about something that there's never time to do. So I'm going to be more specific about what I mean for heatability and, well, this length estimate. So this section is about these macroscopic path properties of the three-dimensional loop-race random walks. So first, let's talk about heatability. I think that the word doesn't even exist, but well, you understand what it means. So here I'm taking a loop-race random walk in 3 dimensions that is large enough. So by large, I mean that I have a ball of radius n, and I start the loop-race random walk on the origin until it hits the boundary of the ball for the first time. So then I get this long path. And now I'm going to consider a point x that is nearby to any point on the trace of gamma. So by nearby, I mean epsilon n. So n was already, well, the radius of the ball where this loop-race random walk is contained, and epsilon n is the distance of this point x to the path gamma. And now I'm going to consider as independent simple random walk. So it will look something like this. And I will let it run up to distance square root of epsilon n. So typically I would expect that this independent simple random walk would hit gamma. But in the case that this doesn't happen, then I would have an escape event. So somehow the simple random walk managed to avoid the path gamma. So the theorem is, well, this is a remarkable theorem of Artem Sapochnikov and Daisuke Shiraishi, is that there exist constants for which the probability that there exists some point here that manages to avoid the loop-race random walk with good probability, well, all this event has a small probability that depends only on epsilon. So here, well, this is a little bit complicated statement because we have several things that are random. So this first probability refers to the probability that I obtain some path. So I could be extremely lucky and I could have like a path that is almost a straight line. So in this bad situation, well, I would have a lot of points that have very good chances to escape from my path. But what this means is that the probability of this kind of bad paths is small, but instead what I get are paths that with that I won't have this high chance of escaping. And here I wanted to be explicit on what is exactly the form of this bound, because this is one of the reasons this result is so useful, is that this upper bound does not depend on n. It of course depends on how far away I took x. So x depends on epsilon, and then, well, I take a square root of epsilon n, how long my simple random walk is going to be there. But this probability is upper bounded by constant epsilon with no n. So this is one of the reasons this is such a powerful tool as we study scaling limits, because it is an estimate that works at all scales. So this is what I mean about heatability. Now I have this other property that are called quasi-loops. So this is what I mean for a quasi-loop. I have my path gamma. So let's imagine I have this thing over here. And I will have a quasi-loop if at any 2 points of my path, let's say x and y, these 2 points are within a ball of radius little r, but the path between them, so it would be all this path, gets out of a ball of radius capital R. So you can see that in the scaling limit, having this sort of situations would be a problem because I would get loops from these simple paths, and there's something that is not desirable. So the theorem that it was proved on the same paper of Artem and Daisuke is that the probability that I have this sort of quasi-loop is, again, very small, depending on epsilon, where little r is equal to some epsilon m delta minus 1, and big R is square root of epsilon delta minus 1. So again, I have this estimate for all scales, and well, this is the small one, and this is going to hold for some constant m that works well when I compare it with a radius of order square root of epsilon with its corresponding normalization. So with very high probability, I do not get these quasi-loops on my path. And now let's talk more about intrinsic length. So now this is the proper statement that Yinon was asking for. So we have that Mn is concentrated above and below by its expected value with very high probability. But here, there is only one problem with this proposition. Well, it's not a problem, but something that we have to be careful for is that this is for Mn, the number of steps starting at 0, which is the origin, until it exits the ball of radius n. So this is between two very specific points. And well, I'm also interested on properties that hold uniformly along the path of my walk. So this is a good start, but we need something more. So let's look what we want. So if I take some 2 points, x and y, and here I'm taking some loop raised random walk gamma that is not too big, but is restricted to some ball of radius lambda Rn. If I have a bound on the diameter of the path between them, so this is the path between x and y, between this loop raised random walk, and well, this path has some diameter. So if I know that this is smaller than Rn, then I can control, well, I want to control, this is what I'm looking for, the number of steps that it takes me to go from x and y. So this is going from Euclidean distance along the path. So this is actually also known as a Schramm distance to the intrinsic distance on the path. So this is some event that we want that the loop raised random walk satisfies this sort of property. And the probability that this is the case is again large. And we have some sort of inverse. So we can say that, well, this is almost equivalent to a key continuity. If I have these 2 points, x and y, and now what I control is intrinsic distance between them. So if it's smaller than n to the beta and this correction lambda b1, then I want to say that the distance between them is not too far, in a sense that as I am walking along my loop raised random walk, I didn't went beyond where I am supposed to go typically according to the growth exponent. So if I can control the intrinsic distance, then I want to control the Euclidean distance as well. So that this happens is, well, that this happens for a particular loop raised random walk is an event. So we're going to call this event E, that we have this control from the intrinsic distance to the Euclidean distance uniformly along the path of our walk. And the proposition is that there exists some exponents for these corrections, lambda b1 and lambda b2, for which this holds with high probability. And again, this is uniformly for all the scales m. So these are the properties of the loop race random walks that we have used before. But now let me show you another instance where we can see this in action. And this is on the proof for the convergence of the subtrees. So the setting here is that we have k points that we fix at the beginning, and we let un to be the uniform spanning tree on our scaled space 2 to the minus n set 3. So then I'm going to consider this sub-tree spanned by the point that I fixed at the beginning on the uniform spanning tree un. So this thing I consider the sub-tree, so it's a collection of curves, and you want to also keep the information of what is the parameterization of these paths along our tree Tn. So well, there's metric space that you can give to these elements, and the law of Tn converges with a metric that takes into account the parameterization of the paths. So let me tell you how to show this proposition. And one idea that we want to implement, we would like to implement, is just to apply Wilson's algorithm. So let's start with some naive version of it. So we're going to simplify things, and we're going to restrict to some box B. And we want to say what is the subtree that we obtain on the uniform spanning tree spanned by x1 and x2 until they reach the boundary of my box B. So consider that we have collections, well, this scale loop race random walks starting at x1 until they exit the ball, and we take the scaling limit, and what we obtain is this curve alpha. So this will be the first step of our intended algorithm. But for a second step, we would like to consider loop race random walks on this new domain, the box minus the trace of our first scaling limit alpha. And now we're in a problem, because what we know about scaling limits of loop race random walks is that they work well on balls and on polyhedrons, but in this situation is not clear what's going to happen because this boundary is fractal-like. So we can say, well, let's cheat a little bit, and now we're going to consider all the cubes of size. This shouldn't be n to the minus r, this should be 2 to the minus r, of size 2 to the minus r, that are actually a little bit bigger than the size of the lattice that I have. So every time that my original path alpha intersects one of these cubes, I add it to this cube that I get. So with this, well, this is a very poor drawing, but I think that you get an idea that I kind of consider a tube, a polyhedral tube that is surrounding alpha, and I call this tube alpha r. So now I want to consider the loop race random walk on this domain B minus this approximation alpha r. So here something that is important is that as I take a scaling limit, n is going to infinity, but r is fixed. So then I am fixing this, this approximation to alpha that is called alpha r, and I consider the scaling limit of the loop race random walks starting at x1 until they intersect, well, alpha r. So they are stopped here. And as you can see, this is not exactly the same as what we're looking for, to be stopped at alpha. So what we want to justify is that if we now take our approximations are better and better, so this would mean that that r goes to infinity, that alpha, well, that this gamma r converges to the real scaling limit gamma that would intersect alpha. So what we want to obtain, if we have this approximation lemma, then this would be the final picture. So this is a rough statement of what this approximation lemma would look like. So this is a picture of my boundaries, alpha S and alpha R. So here we can think of alpha R as a little bit more, as a little bit smaller, and alpha S is a cursor one. And we have our point X2 from which we are going to take loop race random walks. So then we start our loop race random walk until, in this case, it hits alpha S first. So we get walk alpha S. But now we have to hit alpha R. So in this case, well, we for some reason, the loop race random walk didn't go straight to alpha R, but this complicated path. And here, this is the point, the last time that my simple random walk, as I'm generating my second loop race random walk, intersects the past. And then the path that is following is something like this. And this is the path gamma R. So just to clarify, gamma S starts at X2 and goes all the way to the boundary of alpha S. Meanwhile, gamma R starts as well at X2, but instead it goes all the way here. So you can see this purple path is shared, but we have these variations. So we have eta is the path that starts here at the last point of the original simple random walk intersecting the past until it meets alpha R at least. And Gs is the original one. So what we want to justify is that Xi and eta are, well, small, that this is not going to, that most of our curves are on the shared path, the purple ones. So we want to say that Xi and eta are not going to give a big difference on it. And this is a place where we use these path properties of the loop race random walk. So the first one is that we know that the loop race random walk is hittable with high probability, in the sense that I explained at the beginning of the second part. Because remember that both alpha R and alpha S are approximations for some original, well, the first step of our algorithm to generate the simple random walk. So here there is some alpha that is, well, we can actually just take here the loop race random walk. So alpha S and alpha R are approximations to this path that we know that is already hittable. So it means that when I am close here to alpha, the path that I get from the simple random walk cannot be too big. So this implies that the diameter of the simple random walk is small. So it was this, well, a mess of a path that I had as yellow that goes here, and this is the last time that it meets the path of I had built before, and then it continues all the way here. So in particular, if the diameter of this simple random walk is small, then I get that the diameter of eta is also small. So that's the way I control eta. And now I only have to control Xi. So what I know is that this point is on the simple random walk that I know has a small diameter. And also this point is on the same simple random walk because it's the last meeting with the past. So here I know from our quasi-loops estimates. So since we know that there are no quasi-loops with high probability, this implies that she has also a small diameter with high probability. So now I know that eta, well, the diameter of eta is small, the diameter of Xi is small. So the final step is to say, well, if I have control of the shapes, of control of the diameters, I know that with high probability, I also will have control over the intrinsic distances. So what I get is control over intrinsic distances. And this is what I am looking here to control, this distance for parameterized curves that I showed at the beginning. So you can see all these different aspects of the path properties of the Lebre's random walks are what allow us to say that in fact we have this approximation lemma and we can apply Wilson's algorithm as desired. So this is what proves the proposition. And this is the end of the talk. So thank you very much for listening.
Thank you. So we can all unmute to thank Sarai. And I will stop the recording.